Geometric sequence. In a geometric sequence, the ratio between consecutive terms is constant. Now we're talking about ratio. For our arithmetic sequence, we added a number to get from one to the next. That's the common difference, right? Here we are actually going to be multiplying. So in an arithmetic sequence, to get your common difference, you took your second term and you subtracted your first term. That's your common difference. In a geometric sequence, we are looking for a common ratio, something that we are multiplying by. And to get that common ratio, you take your second term and you divide it by your first term. To determine if you have a geometric, you make sure that every step multiplies by the same number. Okay? So we take 15 divided by 5. That gives us what? 3. All right? 45 divided by 15. Also 3. What about 135 divided by 45? Yeah. So this is a geometric sequence. So we would say, yes, this is a geometric sequence. And my common ratio, that's not pretty. My common ratio here is 3. All right. What about B? 30 divided by 15.
2.
45 divided by 30.
1.
Yeah, it's like 1.5, right? So this is not 2. All right. So this is no. It doesn't mean we don't have some type of sequence. It is not a geometric sequence. All right. You may be multiplying or adding. Yeah. So in this case, likely we're adding. Doesn't it look like? And so multiplication definitely doesn't work. If I were to say addition, then we would say, yes, that's going to work. Plus 15 is going to work all the way across. This is an arithmetic sequence, okay? So 1A, right? The first 10 terms of a geometric sequence from example 1. So with this one, oh, that's just a lot. Don't worry about that. Do B and C. Is the sequence arithmetic, geometric, or neither? And explain. B and C. The first one is geometric. The common ratio is -4. -24 divided by 6 is -4. If you apply -4 to every other term, it works. All right. C. Arithmetic. What's your common difference? 12. 12 is your common difference there. All right. Let's look at explicit and recursive formulas for geometric. So we've already talked about arithmetic. Do not confuse these. Arithmetic is a different explicit formula, okay? And in a different recursive formula. For arithmetic, the recursive formula would have been the term in front of it, that's the a sub n minus 1, plus your common difference, right? That's how an arithmetic works. But for a geometric, it is the term in front of it times your common ratio. That's how you get from one term to the next. You take the term in front of it and you multiply it by your common ratio. That is recursive, all right? Recursive means I must have the terms in front of it to get the next term. Explicit. Explicit means I don't need any term except the first one, and then I can give you any term in the sequence. Just jump right to it without walking to it, like recursive. So for explicit, remember for explicit with the arithmetic, you took your first term and you added n minus 1 times your common difference. This is different. We are actually taking that common ratio to a power. So like for the first example, if we had done the 10th term multiplying by 3, by the time we got to our 10th term, we would have multiplied by 3 9 times. The first term is not multiplied by 3, but every term after that would have been multiplied by 3. So the 10th term would have been my first term times 3 9 times. Another way to write times 3 9 times is 3 to the 9th power. All right. So for explicit, for geometric, we are using to a power. We're taking our first term, we are multiplying it by our ratio taken to 1 less than the term we want. And the reason it's 1 less is because our first term is not multiplied by our common ratio. It is just our first term. Okay? So first term times r to the n minus 1. R is your common ratio. N minus 1. N is just whatever term you want. 10th term, 25th term, whatever. All right, so let's look at this. Suppose you want a reduced copy of a photograph. The actual length of the photograph is 10 inches length. The smallest size the copier can make is 64% of the original. Find the length of the photograph after 5 reductions at 64%. 5 reductions at 64%, all right? So the first term is not a reduction. We want 5 terms after our first term. So what term are we actually looking for?
6.
The 6th term. The first term plus 5 reductions. So we are looking for our 6th term in this particular sequence. All right? Our 6th term. Because our original copy and 5 reductions after that. 5 reductions after that. We are going to start with our original. What is the length of our original? Our first term should be what? 10. What is our common ratio? What are we multiplying by every time? 64%, written as a decimal, is 0.64. And this will be taken to the n minus 1, 6 minus 1. So if I were to write this explicit formula without the 6th term, my explicit formula would say, well, my nth term is going to be my original times my ratio to the n minus 1. And so all you do is calculate that. You take 0.64 to the 5th power and you multiply it by 10. So after 5 reductions, the length should be approximately, when you round it, 1.07 inches. This one, I want you to write your explicit formula and find the 19th term. Write your explicit formula and write the 19th term. All right, so your explicit formula. Your explicit formula should have been a sub n, that's always in your explicit formula, equals, what's your first term? 11 times, what is your common ratio? 3 to the n minus 1. That is your explicit formula there. Explicit formula. And then, when you do that, it's this big guy right there.
I did it. Oh, boy, you're in trouble.
So the second one's an arithmetic formula. So for this one, my explicit is going to be a sub n. What's my first term? 20. Plus, I do n minus 1. What is my common difference? 17 minus 20. It's negative 3. Negative 3. And my 19th term here would have been negative 34. So the graphs of the arithmetic and geometric sequence have different shapes. You'll notice that the geometric sharply curves upward because it is an exponential function versus the arithmetic, which is a linear. So arithmetic is a linear. You're going to see a line form when you put down your sequence and see your terms for the sequence of an arithmetic. But this one is exponential, so you'll see it start to shape up like a parabola, like the side of a parabola is what your geometric will look like. All right? You had arithmetic mean, and that was just regular mean, adding the two numbers and dividing by 2. Geometric mean is a little bit different. You're going to take the positive square root of the product of the two numbers. We did geometric mean in geometry. All right? Geometric mean was when we did the right triangles, and it created geometric means, and it was the square root of the product. That's what geometric mean is, no matter where you use it. But in geometry, we introduced geometric mean, the square root of the products, and then we used it in right triangles. All right, and so it's the same definition of geometric mean, the square root of the product. So if you look at this, when a child swings without being pushed, air resistance causes the length of the arc of the swing to increase or to decrease geometrically. Find the missing arc length. All right. They've given us 2 of the arc lengths, and they want the missing one. The first arc length they gave us was 8, and the second one was 6 1/8. So we're going to multiply 8 and 6 1/8. You can get write this as an improper fraction. 8 times 6 is 48. And then over 8, plus 1 over 8 is 49. So we have 8 times 49 over 8. Those 8's cancel. So we just get the square root of 49, which is 7. The missing length here is 7. All right. So go ahead and do the geometric mean of those 3. Check your work. Your missing term for the first one should have been 40. For the second one, 7.5. And the third one, 378. All right, questions on those? All right, we're going to flip back to the beginning, actually right before this section. Page 599 in your books. Page 599 in your books. Fibonacci sequence. We talk about this in geometry. I think we do a short clip of a video in geometry. Fibonacci sequence is a pattern of numbers that is credited to Fibonacci, but it's you're going to see it's obviously way before him. Leonardo Pascal is actually the name of the mathematician. So the sequence itself is 1, 1, 2, 3, 8, 13. So what is the pattern? So if I take 1 and 1, I get 2. 1 and 2, 2 and 3. There we go. And there is the pattern. All right. So what you will find is that this pattern is everywhere in nature. Everywhere. We're about to watch it. But so for example, this pattern of leaves right here, 1, 2, 3, 4, 5, that is the 5th term of Fibonacci sequence. If I count these right here, I am going to get that it is the 13 leaves. It's the 7th term of Fibonacci sequence. This is the 6th term that has 8 leaves. And this last one, of course, is the 4th term. It has 3 leaves. Nautilus shells, pineapples, the pattern in which those are added is in the form of Fibonacci sequence, which is amazing. And so we're going to watch